Okay, lecture 22. We're now in chapter 4, which is going to be mostly solving word problems using calculus. And the first section specifically is a type of problem called related rates. In every single problem, there's going to be 2 or 3 rates given to us. What is a rate? A rate is a derivative. So every problem is going to give us 2 or 3 derivatives. And we need to write down a formula that relates those quantities and then differentiate it, plug in the derivatives they give us, and the answer will fall out. Okay? You're going to hear people say, oh, related rates is the hardest part of Calculus 1. It is not. Okay? It is not that hard. It is hard if you simply want a formula to plug things into. But if you're willing to put in a little bit of thought and be open to it, don't close off your mind and say this is going to be hard. Just try it and see. You're going to see that they're actually not that hard. Okay? Let's do this problem. This is example 1 out of the book. It says, the radius of a circle is growing at a rate of 5 inches per hour. At what rate is the circumference growing? It's not a very long question. I'm going to write it out. The radius of a circle is growing at a rate of 5 inches per hour. At what rate is the circumference growing? Okay, now, in every one of these problems, they will mention 2 or 3 rates. So the first thing is to find that out. Okay? Let's write this here. Let's write first rate. So what's the first rate that they mention in the problem? Let's highlight it. The radius of a circle is growing at a rate of 5 inches per hour. Okay? So in other words, they're telling us the derivative of the radius is 5. Okay? Let's write this down. The radius, let's just say r, okay? Instead of writing the radius, let's just say lowercase r for radius. That's what we usually do, right? When we're talking about circles, we use r for radius. So r is growing. Let's even do this. Instead of writing the word growing, let's just write changing. Because some of the problems, you're going to have things shrinking. So r is changing at a rate of, so what is it? It's 5 inches per hour. Okay, now I want to talk about the units. Here's another thing. Okay, people who always say that this stuff is hard, you look at their paper, you'll probably see that they're not writing down the units. The units make the problem so much easier to do. Okay, but for reasons that I can't say because I don't know, people are so against writing down units, and then it's no surprise that they have a hard time doing the problems because they're not using all the information that they're being given. Okay, look at these units. It says inches per hour. What is measured in inches? Well, in this case, It's the radius is being measured in inches, right? That's a distance. That's the type of measurement. It's a distance measurement, and in this case, that distance is telling us how big the radius is. Okay? It's so many inches. And they're telling us that it is growing at a rate of 5 inches. Okay? For every what? For every hour. Hour is a measurement of what? It's a measurement of time. So this is really important. What they're telling us, just by this right here alone, just by saying inches per hour, what they're telling us is they're telling us that the radius is a function of time. The radius will have a different measurement at different times. So this derivative we could call r prime of t. Or we could call it dr dt, depending on whether you like the prime notation or the Leibniz notation, whichever one you prefer. Now, for me, it's hands down. When I'm doing related rates problems, there's no competition. I like to use the Leibniz notation when I'm doing related rates problems, and I'll tell you why. It's not for an insignificant reason. There's a very good reason why I like to use the Leibniz notation. Because that matches up with the units. You see that? The units are measuring r over measuring t. Inches over hours. The measurement of the radius over the measurement of time. And here I have that in my notation also, r over t. It helps me to keep things set up properly, and sometimes it even helps me to set it up properly in the first place. Okay? All right, so that's one rate that they have given us. Now, there's another rate mentioned in the problem too. Where's that? They don't give it to us, but they mention it. At what rate is the circumference growing? So this is our second rate that's being mentioned. The circumference, let's call that capital C. Capital C is changing at what rate? Okay, so now think about this for a minute. We don't know that number, they didn't tell us, so I'm going to put that at equals question mark. But I still need to write some stuff down here to make sure I do this problem correctly, okay? So, number one, what do you think the units of this rate would be? The circumference is a distance measurement, just like the radius is a distance measurement. And look, they've already told us they are measuring distances in inches. So the circumference would be measured in inches. So the units will be inches per what? It's changing with respect to time. And they've already told us that they are measuring time in hours. So the units will be inches per hour, just like the rate of change for the radius was inches per hour. The rate of change for the circumference will also be inches per hour. Okay, I know it disappeared. I'm going to write it back in a second. There we go. And then the other thing, what would this rate be called? If the rate of change of the radius with respect to time is called dr dt, then what would the rate of change of the circumference with respect to time be called? It would be called dc dt. It's not important if you use a capital C or a lowercase c. I just know that usually in geometry formulas about circles, people usually use capital C for circumference and lowercase r for radius, but that's not a rule. Okay, so you write down the rates that are mentioned. They told us one rate, they mentioned another one, and they asked us to find it. The next step is you have to relate these quantities. You have to write down a relationship between R and C. That's the second step. You write down the rates that are mentioned, and then you write down the relationship between the quantities mentioned. So we want to write down, how is R related to C? Well, that's right, relationship between radius and circumference. All right, well, I hope you know that. The circumference of a circle equals 2 pi times the radius. But if you didn't know, what would you do? Well, I hope you would just look it up. I mean, anybody should be able to find that within like 30 seconds. Okay. Circumference equals 2 pi times the radius. That's the relationship between the circumference of a circle and the radius of the circle. And now we're almost done. Here's what you do. You take that relationship and you differentiate it. Now think about this for a second, okay? We're going to do the derivative of that equation, which means the derivative of both sides, which means we're going to write down the derivative of C equals the derivative of 2 pi r, okay? But the question I have is, when I say derivative, with respect to what? Like, for instance, on the left-hand side I have 2 pi r. Is the derivative of that 2 pi? Well, that's an important question, because the answer might be yes or no. It depends upon what kind of derivative you mean, because remember, even though people don't always say it, it's still an important piece of information that when you do the derivative, you have to know derivative with respect to what. Now, when I see that 2 pi r, if I wanted to find the derivative with respect to r, then the answer would be 2 pi. But I think you can probably guess that I don't want to do the derivative with respect to r, because look at both rates that I've written down. They are both derivatives with respect to t. So when I do the derivative of this equation, I want to do the derivative with respect to t. Are there any t's there? No, there's not. But circumference is a function of time, and radius is a function of time, and I'm going to do the derivative with respect to time. Have we done something like that before? That's really just implicit differentiation. And on the left, I have only what? Just c. And I want to do the derivative with respect to time. And what will I get? I will get the derivative of c with respect to time. That's pretty straightforward, I think. The other side, we have 2 pi r. 2 is a constant. pi is a constant, r is a variable, and r is a function of time, because r will be a different measurement at different times. So when I do the derivative of 2 pi r with respect to t, I get 2 pi times the derivative of r. Now, if you really, really like the prime notation instead, then what would it look like? It would look like this. C prime of t equals 2 pi times r prime of t. But I hope that you see what I was talking about, that the Leibniz notation will really save your hide sometimes because of how it matches up with the units, which means that the units which will be given to you in the problem, there will be units. And if you look at the units, they will tell you what kind of derivative you need to do. In this problem, I see the units are inches per hour, and so I instantly know I'm doing derivative with respect to time, because hour is a measurement of time. Okay? All right, so what do we do now? Well, we plug in the information they gave us. Look at this. Do I know how big 2 is? Yes, 2 is 2. Do I know how big pi is? Yes. Do I know how big dr dt is? Yes. Because why? Because they told me it's right here. Do I know how big dc dt is? No, but that's what they asked me for. So what I'm saying is this. You take what they give you and you plug it in. They gave us this, dr dt equals 5 inches per hour, so I just plug that in, and I get dc dt equals 2 pi times 5 inches per hour. What's my answer? My answer is 10 pi inches per hour. There's our answer. That's how fast the radius is changing. Is it a positive or a negative rate of change? 10 pi is positive. So that means the circumference is growing, which is what they asked. At what rate is it growing? And the answer is 10 pi inches per hour. Without the units, the answer is incomplete. If you just say, how fast is it growing? 10 pi. That has zero meaning. Unless you say 10 pi what? Because 10 pi inches per hour, that's one rate of growth. It's not a particularly fast growth. But 10 pi millimeters per second is extremely fast. So just saying 10 pi tells me absolutely nothing unless you also say what the units are. And most people, I got to tell you, most people will leave the units out and then try to just put them onto the answer. And once again, those are the people who will tell you that this stuff's really hard because they're not using all the information they're given. They're trying to do the problem with as little writing as possible, and guess what? They find the problems very difficult. Okay? But I think if you're being honest with yourself, and you look at what we just did here, I think it's hard to say that this was difficult, if you're being honest with yourself. They gave us one rate, we wrote it down. They asked us to find another rate. We wrote that rate down. We wrote down the relationship between those two quantities, did the derivative of both sides, plugged in the number they gave us, and there's our answer. Not that much is involved. Are there harder problems than this? Yes. I mean, some of the problems will be harder than this, but they'll all follow the same pattern. You do this, you do this, you do this, and then you differentiate and plug in. It's the same pattern for every single problem. Okay? Some problems will have 3 rates instead of 2, but it's the same idea for every single problem. Okay, let's do the next one. Okay, this one says water streams out of a faucet at a rate of 2 cubic inches per second onto a flat surface at a constant rate, forming a circular puddle 1/8 of an inch deep. At what rate is the area of the puddle growing? And at what rate is the radius of the puddle growing? Okay, so I'm going to write these down. Water streams out of a faucet at a rate of 2 cubic inches per second onto a flat surface that's not how you spell surface. At a constant rate, which is redundant, to be honest with you. I don't know why they said at a constant rate, because they already told us the rate, and it's 2. And what's 2? 2 is a constant, so I'm not sure why they felt the need to say that when they've already shown us that. But nonetheless, it's in the problem, so I'm writing it down, okay? And then it says, forming a circular puddle that is 1/8 of an inch deep. Okay, and there's 2 questions. At what rate is the area of the puddle growing? And the second question says, at what rate is the area of the circle growing? The circle and the puddle are the same thing, because the puddle is a circle. At what rate is the radius of the circle growing? Now, if at all possible, I would suggest that you draw a picture, because if you can see it, it makes things much easier. Okay? So I'm going to draw a picture of this. Boom, there you go. Okay, now, what do we have going on here? The water is coming out. Okay, at what rate? They tell us that. Here it is. 2 cubic inches per second. Okay, so let's write this down. 2 cubic inches per second. Now that's the rate of the water coming out, so that's a derivative. So that is d something with respect to something. Okay, this is important. This is what makes the problems be not that hard, is if you can Figure out how to use the units, okay? So let's think about this. The top is cubic inches. What kind of a measurement is cubic inches? Is that a length? Is it an area? Is it a volume? What is it? The fact that it's cubic means it's a volume, right? So what they've told us that 2 cubic inches per second, that's the derivative of a volume of water. With respect to what? Well, that part now I hope is pretty straightforward because it's just like last time. Seconds is on the bottom. Last time it was hours, this time it's seconds, but they're both measurements of what? Those are both ways of measuring time. So they have told us the derivative of the volume of water. Okay? Now, all of that water is coming into this puddle down here. Okay, what's the shape of that puddle? In real life, it wouldn't be this perfect shape, but based upon what they've given us, that says what? A circular puddle. So I drew a circle, and it's 1/8 of an inch deep. So that means this right here. Let me erase this gray line. We don't really need that. That means this thickness or depth or height, whatever you want to call it, that's 1/8 of an inch. What do you call this kind of shape right here? That's a circle when you look straight down at it from the top, but it has a thickness to it. What do you call that? That's called a cylinder, right? And what else should I mark here? So I want you to look at the questions they're going to ask, okay? The first question says, at what rate is the area of the puddle growing? What do they mean by that? Area. They mean the area of this circle on top. So the first question is asking us for, let's go ahead and write this down. The first question is asking us, at what rate is the area growing? They're asking us for the derivative of the area. What's that shape? It's a circle. Do you know how to find the area of a circle? Sure. The area of a circle is pi r squared. Okay. All right, that's going to be the first question. I know I didn't actually write anything down in blue, but we will in a minute. Okay, now, the second question, B. What are they asking us for there? At what rate is the radius of the circle growing? So, that's this radius. Okay? And they want us to find the derivative of radius in question B. All right, so here's what we're going to do. Just like last time, okay? We write down the rates that are mentioned. Ones that they tell us and ones that they ask for. Okay? So, for question A, the first rate that we have is one that they gave us. They told us the rate of change of the volume. By the way, that water is coming out of the faucet at a rate of 2 cubic inches per second. All of that water is going into this cylinder, so that means the volume of water coming out of the faucet is going into the cylinder, so the volume of the cylinder is growing at a rate of how much? 2 cubic inches per second, because that's how much volume is coming out of the faucet. Okay? All right. So the first rate is one that they gave us. They told us that the derivative of volume with respect to time is 2 cubic inches per second. What's the second rate in problem A? Well, they didn't give us any more rates. So the second rate that's mentioned is the one they asked for, which is at what rate is the area of the circle growing? So in other words, they're asking us to find dA dt. I don't know what it is, so I'm going to put question mark. But I am going to write down the units. If volume is being measured in cubic inches, what would you measure an area in? Well, that would be in square inches. Okay, and they've already shown us what time is being measured in. It's being measured in seconds. So even though I don't know the numerical part of the answer yet, I'm going to go ahead and write down the units part because I already know what it's going to be. It's going to be square inches per second. Okay, and now what did I say as the third part? Look up at this problem again. So we wrote down the first rate, we wrote down the second rate. The next step is find a relationship between those quantities. Okay, so let's go down here. What are our quantities that we're talking about? We're talking about volume. That's the volume of water that's coming out of the faucet, which means it's also the volume of the puddle, which is a cylinder. So that's the volume of a cylinder. And the other quantity is the area of the circle on the top of the cylinder. So I need a relationship between the volume of a cylinder and the area on top. Okay? How am I going to find that relationship? Well, how about if we start by just doing, here, let me write this down by the way, relationship between V and A. So where should I start? Well, the first derivative is the derivative of volume, and the shape I'm looking at is a cylinder. So I'm going to start by writing down how you find the volume of a cylinder. Okay, let's write that down. The volume of a cylinder is equal to pi r squared times h. And again, if you didn't know that, what would you do? You would look it up. I don't expect you to remember everything you've learned in your life. Okay, if you don't remember how to find the volume of a cylinder, you can look it up. Okay, now I'm trying to find a relationship between volume and this area up here. Well, remember, what's the area of that circle? Area of a circle is pi r squared, right? Isn't that right here? So don't I have that volume equals the area of the circle times the height? I think I do. I think that's what I have. You see what I'm saying? Because that pi r squared, that's the area of the circle at the top of the cylinder, and also at the bottom, but you can't see the circle on the bottom because it's sitting on the countertop. So there's our relationship between volume and area. And then what do we do? Implicit differentiation. So we get, it should be blue, oh, that is blue, dV dt equals dA dt times, well, that's a good question. I'm going to ask you a question. Do I need the product rule here? Let's think about that. Should I write the derivative of A times H plus A times the derivative of H? Should I write that? That's the product rule. Well, the answer to that is it's fine if I do, but I don't have to. Okay, that might sound confusing. Let me explain. So, number one, here's what's important. H is not changing. Let me zoom in here so you can see H again. This is H right here, the height of the cylinder. That's H. It's not changing. How do I know it's not changing? Because in the problem it says the circular puddle is 1/8 of an inch deep. It doesn't say that that is changing. Okay? So, H is 1/8 of an inch. 1/8 is a constant or variable? It's a constant. So H is a constant. So when I do the derivative of A times H, I just get the derivative of A times H. Because H is not a function of t. It's not changing over time. It is a constant. Just like if you had x times 5 and you wanted to find the derivative with respect to x, you would have what? 1 times 5 would be the answer. You see what I'm saying? Now, what if you're saying, oh man, I don't know if I can remember that. Well, then let me show you something. Suppose you did not realize that H is a constant. What if you looked at this and you said, oh, I need to do the product rule. So I do the derivative of A times H plus A times the derivative of H. Are you doing the problem wrong? No, that's fine. Because here's what you're going to do in the next step. We're going to fill in what's given to us. And what are we going to put right there? How fast is the height changing? It's not changing at all, is it? So what am I going to plug in there? I'm going to plug in a 0. And that's going to disappear. And you'll be right back to what I said. That's all you need to write down. You see what I'm saying? So, either way, we're going to end up with this. dv dt equals dA dt times H. Okay? Plug in what we're given. What are we given? We're told that this is 2 cubic inches per second. We're told that this is 1/8 of an inch. So let's plug those in. 2 cubic inches per second equals dA dt times 1/8 of an inch. I'm trying to find dA dt. Can I find it? Sure. What's it going to equal? The numerical part's going to be 16, isn't it? Why is that? You multiply both sides by 8. These 8's cancel out. On the left you have 8 times 2, and that's 16. What are the units? Well, you can guess at the units, or you can calculate the units. You can say this. Well, let's see. I'm finding the derivative of area, and area would be square inches, so the top of the units has to be square inches. It's the derivative with respect to time, and time is being measured in seconds, so the bottom of the units has to be seconds. You can figure it out that way. Or you can just do this. You can treat the units just like you would treat, let's say, a variable. I canceled out the 1/8 by multiplying both sides by 8, right? Well, look what else I can do. I can cancel out the word inches by dividing both sides by the word inches. And what's going to happen, let's see if I can squeeze this in here. I'm just going to move this over. What's going to happen is you're going to get inches down here on the bottom. I would never let anybody hear me say, I divided both sides by inches, because inches is a word, not a number. I can't divide by a word. but it's just like that. It is as though I divided both sides by inches, and what's going to happen? I have inches to the power 3 divided by inches to the power 1. What do you end up with? Inches to the power 2 on the top. Okay? So you don't have to try to figure out what the units should be. Just look at the math and see what the units come out to be. And then I would suggest this. Then look at your answer and see if the units make sense. Well, square inches per second makes total sense, because on top I have area, and area would be measured in square inches. On the bottom I have time, and time would be measured in seconds. Okay? So that's, again, I don't think that that is a hard problem. Is it harder than what we've done so far? Maybe so. That's true, if I'm being honest. But just because it's harder than the stuff we've done before doesn't mean that it's hard, right? I mean, a sponge is harder than air, but that doesn't mean that a sponge is hard, right? Okay, now let's do B. Well, there's not very much to do because we're almost done. What would I do? I would write down the first rate. I've already done that. I would write down the second rate. I've already done that. Write down the relationship between the quantities. I already did that. The only thing for part B, the only thing to notice is they're asking us for at what rate is the radius growing. So they're asking us for what? dr dt. So I should actually do this. So I won't erase everything because so much of it's going to be the same. We'll save time by keeping it written down. I'll just erase that A and put B. So the only thing that's different here, if you allow me to erase our math so I can go back to the setup of the problem. Okay, what's different here is the second rate is not dA dt, because they're not asking us for the change of the area this time. They're asking us for the change of the radius. So I'm going to write dr dt. What would the units be then? The radius would not be measured in square inches, right? It would just be measured in inches. So the units should be inches per second. And I need to write down a relationship between V and R. Don't we already have that written down? We already have V equals pi r squared times h. All right, all I need to do is the derivative with respect to t. We're going to get dv dt on the left, and on the right, pi is a constant, so that's not going to change when I do the derivative. H is a constant, so that's not going to change when I do the derivative. R is a function of t, so when I do the derivative of r squared, I'm going to get 2r r prime. Does that make sense? I hope that's not squeezed in too much here. This is the derivative of pi is pi. Sorry, that's not true. I shouldn't say the derivative of pi is pi. What I should say is what I said before. Pi is a constant. And so when I do the derivative of this whole thing, I'm not doing the derivative of pi, I'm doing the derivative of this whole thing. Because pi is a constant, it won't change. And because h is a constant, it won't change. But the derivative of r squared would be 2r times the derivative of r. Right? Remember from implicit differentiation? You might prefer to write v prime t equals pi times 2r r prime times h. Okay. All right, now let's plug in what we've been given. What were we given in the problem? The only thing we were given is that the derivative of v is 2 cubic inches per second. That's all I've been, oh, and sorry, we're also being given h is 1/8 of an inch. So let's plug those in. 2 cubic inches per second equals pi times 2 times r prime times 1/8 of an inch. And we're trying to find r prime. So I need to divide both sides by pi, divide both sides by 2, divide both sides by r, even though I don't know how big the radius is. That's okay. I'm just going to divide both sides by r and multiply both sides by 8, right? Do you agree with that? What are you going to come out with if you do that on the left? Don't worry about the units yet. Do you agree that you're going to come out with 8 over pi r? Do you agree with that? Because the 2's canceled. The pi and the r we divided by 2, and that's why the 2's canceled. We divided by pi and also r, and that's why they ended up on the bottom. We multiplied both sides by 8, and that's why there's an 8 on top. Okay. What's left on the right side? dr dt. What are the units going to be? Well, I did have cubic inches per second. Here's inch. So what will you end up with? Just based upon that, you will end up with square inches per second, right? Just like before. So let's write that down. And then what did I say I would do? I would ask yourself, does that make sense? Should the derivative of radius be square inches per second? It actually shouldn't. Radius is not measured in square inches. It's just measured in inches. Why do I have square inches? I should just have inches. Well, here's the reason why. This guy, r. That's the radius of the circle, which they didn't tell us, so that's okay. I don't have a number to plug in there, so I just leave it as r. Don't let that bother you, okay? If they said the radius is 38, then I would have plugged in 38. But here's the key about the units. If they did say the radius was 38, they would say 38 what? They'd say 38 inches, right? And so down here I would write 38 inches. And wouldn't that cancel out one of the inches up here in the inches squared? So what I'm saying is this. That r right there is actually a certain number of inches. So when we divided both sides by r, it would be as though I am dividing also by the word inches. So let's just go back to the number 38, because I just said an off-the-cuff remark. I said, what if the radius was 38? So then right there for the r, I would put 38 inches, and we would divide both sides by 38 inches, and the 38 would end up on the bottom, and I would have one more inches to divide by. That one and that one. So let me just make this clear. This is a number of inches, and this is a number of inches. And they're being multiplied together. So on the right, I have inches squared. So when I divide both sides by that, I will be dividing by inches squared. Okay? Inches cubed divided by inches squared is inches. Okay? And so here's our answer then. The radius of the circle is growing at that rate. 8 divided by pi times whatever the radius is. Inches per second. Okay? If you wanted to know how fast the radius is growing, you would have to measure the radius at that moment of time and see how big it is, and then you could plug that number in right here, and then you would be able to calculate how fast the radius is growing. So again, this is harder than what we've done in the past, but I would not go so far as to call it hard. And I'm making a big deal about that only because I know that people walk around the hallways saying, oh, related rates is so hard. And you're going to hear that. And I'm trying to tell you to just blow that off. Don't let those people influence you, because I don't think they're correct, number one. And number two, the only reason they think it's hard is because, in my opinion, two things. Either they let other people influence them, and so they believed that it's hard, or they're trying to do the problems without using the Leibniz notation and without using the units. So they're really trying to do the problem in as cheap and fast of a way as they can, and they're getting confused because they're not using the information that's being given to them. Okay? I think if you use the information that's given and you don't listen to people telling you negative thoughts, I think you'll find that this stuff isn't really that bad. To be honest with you, this is my favorite section of the whole book. I think of Calculus 1 and Calculus 2 together. I think this is my favorite stuff because it's useful. You can actually answer a question this way. Now you might say, well, why would I care how big a puddle's growing? The point isn't why would I care. The point is that I can answer that question using math. And to me, that's interesting and that's exciting. If you can't use this to actually answer questions, then why are we even learning it? You know what I mean? Okay, this has been how long of a video here? Almost an hour. So I'm going to stop, and then in the next video, we're going to do more questions of the same type.